All right, this video covers a Fourier Series assignment that I'd like you to work on. And what we're going to do in this assignment is take a look at applying Fourier Series to any given waveform. So I start here with a couple of examples. One example is x of t. X of t is rectangular pulses that are extended periodically. And then y of t is a triangle pulse that's extended periodically. So we're going to calculate the Fourier series on that. I'm going to show you some Matlab code that will do that. And then I'm going to ask you to apply this to a different waveform. All right, so let's start with x of t. All right, one of the things we know about Fourier series is that x of t, since it's periodic, can be written in the complex exponential form Fourier series. Okay, so n equals minus infinity to infinity. Cn's, these are the Fourier series coefficients, e to the j n omega naught t. All right, where omega naught is the fundamental period, which is fundamental frequency, which is 2 pi over cap t, where cap t is the fundamental period. Okay, so what we know about this is that we can find Cn by applying the Fourier series formula, the synthesis formula. So in that, I take 1 over t, integrate over any period of the waveform, and then multiply by e to the minus j n omega naught t dt. All right. So in this demo, we're using Matlab to symbolically calculate this expression for the Fourier series coefficients. So we're going to do this integral symbolically, and then you can evaluate all the coefficients. You'll have the Cn's. All right. Another thing we want to do in Matlab is actually plot a truncated Fourier series. All right. So when we plot Fourier series, it's easier. I mean, we could do this complex exponential form, but we have complex numbers floating around. It's easier if we can keep things real. We know the ultimate result is, a real signal. So for that, what we're doing in the demo is we're representing this with the compact trig form of the Fourier series. Okay, so in the compact trig form, you have the DC component C0 plus the sum from n equal 1 to infinity of the magnitude of the Cn's times 2 cosine n omega naught t plus the angle of the Cn's. All right, so this is compact trig form. Everything is real. It's a little bit easier to do plots using Matlab, using the compact trig form. Okay, well, we have a practical problem in doing a computer code to plot this signal. The practical problem is sum from n equal 1 to infinity. Of course, we can't go to infinity. All right, so we have to approximate this. All right, so x of t as an approximation, so I'll put a tilde over the top. That would be C0 plus the sum from n equal 1 to cap n of 2 Cn cosine n omega naught t plus the angle of Cn. All right, so the difference here is we're going to stop at some value n, go from 1 to n. All right, so in a second here, I'm going to pull up some Matlab code and show you how this works. We're going to apply this to the rectangular waveform, and then we're going to also apply it to this triangle pulse waveform. So ultimately, the reason I wanted to do two waveforms is that you'll see, yes, the Fourier series converges. Actually, it converges in mean squared error. We'll have to talk about that later in the course, but it converges perfectly fine for these rectangular pulses, but you're going to see the well-known Gibbs effect, where at the point of discontinuity there's a little bit of ringing that happens when you plot the Fourier series. Okay, so on to the Matlab code. Here's Matlab code that I'm going to give you, and all you'll really need to do is change the symbolic integration to fit the function that I'm going to give you. But I wanted to go over this code, and your task as engineers is to look at the code and make sure you understand where it's coming from and learn from it, because we're going to do things like this throughout the class. Alright, so the first thing I'm doing in this code is I'm using the symbolic toolbox. So there's several variables that I'm using here. Some of them are just to show you how to use the symbolic toolbox. So for example, starting out, I wanted to show you that you can do symbolic integration. The function for that is int, and the first argument is the integrand, the thing you want to integrate. The second argument is the variable of integration. You can add definite limits, but this is going to calculate an indefinite integral. So when you hit run, it will run through there and update and give you this as the answer. So watch my mouse. That's the answer for this integral. Alright, so from here, remember we're doing a Fourier series, and we have a certain number of terms that we're going to add in the approximation of the Fourier series. Remember this technically the series goes from 1 to infinity. So let's start out with just a few terms. Let's start out with 5 terms. And here is, tau is going to be 2, cap t is going to be 4. Go back in the video to see, where those parameters kick in. But this is the integral that you need to solve for the Fourier series coefficients. Okay, let's run this and take a look at their output. Okay, so when I run this with only 5 terms, what I'm getting on the output is, I have to slide this around a little bit. Okay, it snapped. I didn't want that. Okay, so this shows you a plot of the Fourier series coefficients. At n equals 0, that's the most energy, and then the first harmonic. Actually, these are frequencies that are plotted down here. So these are harmonics, n, f naught basically, and then you can see with just a few harmonics, this doesn't really look like a rectangular pulse yet. It's starting to shape up, but it's not quite there. So if I, this is off the screen, but I'm going to go and change this to 10 and rerun it. Okay, so when I change that to 10, you get more terms in the Fourier series, and it's starting to shape up like a rectangular pulse. Okay, let's see if I can get everything on here without it snapping. Okay. So then if I change this to 40 terms and rerun this, this starts to look more and more like the rectangular pulse. But what I alluded to when I first started the discussion about the rectangular pulse was, if you look at this and zoom in, you see this ringing effect that shows up whenever you have a point of discontinuity. This is the Gibbs phenomenon. You probably talked about that in your signals and systems class. Okay, so that always kind of bugged me. The Gibbs phenomenon kind of bugged me when I was a student, but it really only happens at the points of discontinuity. As you let the number of terms go to infinity, the size of the ringing in the middle shrinks down to 0. However, at the point of discontinuity, the ringing is always there. Okay, so I also wanted to show you a case where there's less ringing. Okay, so when you have a triangle pulse, there's no point of discontinuity, so the Gibbs effect is not in play. All right, so your task is to study this integral, how I set this up, look at the code and verify that that's what you would expect to get when you set up the integral for this Fourier series. All right, so I'm going to rerun this. Let's start with fewer terms. Let's start with just maybe 5 terms and see what happens. All right, so you see the Fourier series coefficients plotted. It's starting to look like triangle pulses, but it's, the edges are lost, and you still have this ringing down in here. But there's only 5 terms. Okay, so if I add a lot of terms, let's say 60 terms, and rerun this, indeed, it starts to look like the triangle pulses. All right, so that's part of the point of the assignment. The other thing is I want to go over some of the details of how this code works. We did in this step a symbolic integration. So C is actually a symbolic variable at this point. And from there, I'm assigning the harmonics. Okay, so I know that I'm going to add up the first 1 to n harmonics. 0 is included because 0 is the DC term. And then I do this little fudge where I know that n equals 0. When I do that integral, there's a division by n, and at n equals 0, this would have a divide by 0 problem. And so I just add a little offset. It's a numerical trick. The results are less accurate, but it's still close enough for what we're doing here. All right, so if I was going to be more careful with that, I would separate out that n equals 0 case and probably either calculate that by hand, put that in the code, or do something different where it's not affecting all the harmonics. But it works for our purposes here. All right, the next thing that I'm doing here that you should know about is with this particular command, I'm converting the symbolic variable to a double precision, just a regular Matlab variable. That way I can do plots, all right? I can take a look at the Fourier series coefficients, and I can put this for loop in that calculates the Fourier series, all right? So down here you see this for loop. We're adding in every term. I have 2 times absolute value of C, the CKs, plus cosine 2 pi k, so forth and so on. Notice if you're paying attention to details, there's a k plus 1 here. All right, and so the reason that's there is MATLAB starts its indexing at 1 instead of 0. If MATLAB could start at 0, I wouldn't have to do this. All right, but I have everything, all the Fourier series coefficients offset by 1. So for example, C of 0, mathematically the C0 is actually the Matlab variable C1. All right, so I have to add this k plus 1 term in everywhere. All right, so for your homework, really you just have to change this expression, and what I would like you to do is from there just print the result and turn it in on Gradescope. I'll give you more details about that when we talk about it in class.